Hello YouTube. If you're watching this, I'm assuming you want to know all about thermodynamic equilibrium and that you are ecstatic to get on your journey to understanding separations. Now this is my first video in a series on distillation or separations in a more general term. And the reason that I'm starting with thermodynamic equilibrium as opposed to, let's say, straight into a distillation column is because without understanding what thermodynamic equilibrium is, it really is impossible to move on in distillation. The thermodynamic equilibrium assumption is key to understanding distillation columns. So this first video is just going to be brief, and it's on what is thermodynamic equilibrium. And the thing to remember is that there's three important equilibriums that must be reached in order to achieve thermodynamic equilibrium. The first one, very easy, is temperature or thermal equilibrium. So let me write that down. So number one, we have temperature or thermal equilibrium. So this is not very difficult. If you, let's say you have two objects touching each other. You get to use colors here. See if this shows up or not. Whoops. There we go. Okay. So guess which one is hot? It's the red one, right? If you have, let's say, a hot temperature here, T hot, T cold, we know that the temperature will flow hot to cold, or the energy will flow hot to cold. It's going to seek that lower Gibbs free energy. And so thermodynamic equilibrium is when the temperature of an object does not change with time. So if we look at our very ugly example here, eventually if these two objects are left touching each other, we'll say for eternity, for infinity, then the two objects will have the same temperature. And when two objects have the same temperature, the temperature is no longer changing. That is temperature or thermal equilibrium. So you can think of it as being the derivative of the temperature, dt over dt, is equal to 0. The temperature is no longer changing with time. Okay, moving on. The second type of equilibrium is mechanical equilibrium, but you can think of it just being as pressure equilibrium. The two pressures are equal. So we'll write mechanical or pressure equilibrium. And at this point, as you may find yourself in situations if you work as a chemical engineer where you're looking at a fired heater. Now, a fired heater, how it works is you have the fuel-air mixture coming in the bottom. So we'll draw a very poor diagram here. Okay, so we'll say that fuel, air, they come in the bottom. You have burners, several of them, little flames, and there's viewports on the sides. Viewport, literally a little latch you can go up to as your little person, and you can open the viewport and look inside. And you can do this even though they can be up to, I don't know, 13, you know, very high temperatures, we'll say 1300 degrees Fahrenheit inside. You can open those viewports and look in because of this, because of the pressure difference. The fired heaters, they can have a damper, and you can open or close this to adjust what they call the draft. And what draft basically is just the negative pressure you're operating the heater at. So you can look inside, and if you put your hand right up to the viewport, you'll actually feel air rushing in from the outside. And what this does is assist in control of the fired heater, but it's an example of that. It's not at pressure equilibrium or mechanical equilibrium. If it was, there would be no air traveling in or out of the fired heater. But because because it's at negative pressure, air rushes in. So we can think of that mechanical or pressure equilibrium much the same way as temperature or thermal, in that the dP, if you look at the change in pressure or change in time, is equal to 0. Okay. So I promised 3, we got 1 and 2. The last one is the chemical equilibrium. And this one isn't as intuitive as temperature or mechanical. The chemical equilibrium requires that instead of the temperatures and the pressures being equal, it requires the chemical potentials to be equal. So we'll say chemical equilibrium. Okay, and chemical equilibrium is written as a mu. So we'll just say, what will we say here? We'll say, for example, mu I liquid equals mu I vapor. But that's more of a specific example to the dual phase equilibrium. But what we're going to be talking in more general terms is just saying the chemical potentials are equal. And what chemical potential is, I would suggest if you really want to dive in deep to look up a different video, because I'm just going to cover it very briefly. But chemical potential, if you want to look at the actual thermodynamic definition, it would be the mu, which is the units of it can be joules per mole, R joules per mole, is equal to U plus PV minus TS. And this can also be equal to, as if you're really good at your thermo, you already knew this, the enthalpy minus TS. And you might recognize that as your Gibbs free energy. And so, just as in temperature or in pressure, where you find the energy wanting to travel from high to low, the chemical equilibrium will want to go from high to low. You want to minimize that Gibbs free energy. Many of you will have heard that concept before. And what U depends on is interesting. You can see that right here, the chemical potential depends on pressure and temperature. So if the temperature or the pressure is changing, so you don't have equilibrium of temperature and mechanical, then you definitely don't have chemical equilibrium as well. What mu depends on, what chemical potential depends on, is temperature, pressure, as I already said, but also it depends on, so we got T, P, your phase, so we're talking liquid, volume, solid, and concentrations. For this reason, if someone sprays perfume in a room, the chemical potential will be imbalanced. It'll have a high chemical potential close to where the perfume was sprayed and low chemical potential in other areas of the room. That chemical potential is going to want to spread out. It's going to want to reach equilibrium. So that's why even though that will literally spread throughout the room, those perfume particles. Okay, so we can think about this as well, saying that the d mu over dt is equal to 0. So if you want thermodynamic equilibrium, you have to have all three of these values. So if you have thermodynamic equilibrium, you could say that the dt over dt is equal to the dp over dt is equal to the d mu over dt is equal to 0. So what that is saying is basically that the dt, the temperature, the pressure, and the chemical potential, if they are not changing with time, they're constant, then you are at thermodynamic equilibrium. Okay, that was what I thought was brief, maybe thought it was too long. Hopefully you can watch it in double speed so you can skip through all the parts where I muddled through. But if you liked it, please give me a thumbs up, and there will be a lot more videos coming. So this is going to be all about distillation, helping all my fellow or aspiring engineers. Thank you.